Hi there, and welcome to the next module in the AI Developer Bootcamp. My name is James, and in this session, we're going to look at the fundamentals of neural networks and how Microsoft's Deep Learning Toolkit, Cognitive Toolkit, can help us build these types of solutions. So, when would you need to build your own deep learning model? When would you need to use Microsoft's Cognitive Toolkit? Well, the first thing to point out is that the litware demo didn't require any custom deep learning models. All they used were the cognitive services that we've talked about so far. Having said that, many of the cognitive services that are available to you use deep learning and deep neural networks as their basis. So if you want to build something similar, if you want to build your own cognitive service that's specific to your problem domain, then you're probably going to need a toolkit like the Cognitive Toolkit. So if you want to add a feature that's simply not supported, an AI feature that is not supported by one of the major cloud providers, then you're probably going to have to build it yourself. And in this session, we're going to look at the different approaches to doing that. So, what is the Cognitive Toolkit? What can it enable? And how do we use it? Before we go any further, a warning. This is not for the faint of heart. You'll need to have an understanding of the fundamentals of neural networks and a solid mathematical background. This will require a significant investment in time and money from your organizations to build and productionize these kinds of models, but the payoffs can be considerable. The terms that we use when we talk about deep neural networks are going to be much more familiar to data scientists and statisticians than they are to developers. Building these kinds of models is a specialized skill, and the point of today's session is not to make you an expert. Instead, it's going to introduce you to the fundamental principles that have unlocked this exciting area of research. As we mentioned right back in the first module, one of the unusual characteristics of neural networks compared to many other machine learning techniques is that they can become more and more effective as they are exposed to more and more data. They are able to recognize surprisingly complex concepts and patterns, and they can become unreasonably effective if constructed correctly. So, now in the last session of this bootcamp, we're going to talk about what specifically a neural network actually is. So one forcing function that I like to use before starting along a machine learning journey is to understand whether I can fit the data into a spreadsheet. Because typically, if you can get your data into a spreadsheet, it's in a good place for machine learning. So what do I mean by this? Well, you'll see here a table or a spreadsheet that has some examples in it. It has a group of people. We have their age, their income, their education, and their gender. And out of that data, we want to be able to predict what kind of housing they use, whether they own their home, whether they rent, or they have some other arrangement. And we want to build a network that allows us to take those 4 columns, age, income, gender, and education, and predict housing. So the first 4 columns are what we know. Depending on who you talk to in data science, these are called different things. They might be referred to as features, attributes, or potentially other names. And then the thing to predict is the class or the label. So those first 4 columns in the spreadsheet are what we know. The last column is what we predict. And if you can format your data in such a structure, then chances are you've got a good chance of getting a reasonable outcome from machine learning. So what is a neural network then? The first thing we're going to look at are the inputs to the network. And in this case, it's going to be each of the features in our spreadsheet. So age, income, education, and gender. The thing to know about a neural network is that it's just a big mathematical equation. So when we have text like education or a category like gender, then we need to be able to convert that into a number. There are a number of different patterns for converting text and various values like large numbers into numbers that are suitable for neural networks. And that in and of itself is a session. However, for the purposes of today, we're going to use a range of different techniques to convert these text values and large numbers into something suitable for neural networks. Each of these numbers is then going to form an input into our network. The output layer of the network is going to reflect the different categories that the network seeks to identify. We have three categories to consider: owning a house, renting a house, or some other situation. And for the purposes of this discussion, we can consider these outputs to be probabilities. So we're going to get three numbers out of this network: the probability of renting, the probability of owning, the probability of another situation being the case. So we have each of the features, the things that we know about the person, as inputs, and we have probabilities of each of the categories as the output. You may now say, what is the middle bit? Where does the magic happen? Let's go and have a look at that. Let's take this example. We have three inputs: 0.1, 0.2, 0.3. These are the numbers. This is what we know. These all go into a node in the neural network, and this is referred to as a perceptron. Each of these numbers, these inputs, are multiplied by a weight. Each of the connections from the input to this node has a weight associated with it. So the maths behind this is actually relatively simple. We take the input, we multiply it by the weight, and then we add up all of the individual inputs. The next thing we do is we add a bias to the node. And again, this is just simple addition. And then the last thing we do is we run that result through an activation function. And we'll talk a little bit more about activation functions later. But fundamentally, activation functions allow us and allow the network to actually start to build non-linear concepts into its structure. Up until now, it's just been linear algebra. And that's really the fundamental pattern of a neural network. We have a bunch of inputs. Each input is multiplied by a weight. A bias is added, and the output is run through an activation function. So at this point, you're probably reflecting on neural networks as something that is relatively simple. And they are. Fundamentally, they're just mathematical equations. However, as you start to get more and more complex structures, trying to understand more and more complex data like voice, these can become quite difficult to manage and design. So there are a number of questions that you need to be able to answer when you're building your neural network. For example, how do you encode your inputs so they're numbers? How many layers within the neural network do you have between the input and the output? And in many cases, this requires experimentation. We also need to identify what activation function that we use. There are many, and they have different characteristics and work well in different scenarios. And then we need to be able to actually identify where those biases and weights come from. The network will get initialized depending on the approach that you take with some default weights. And then as we run more and more training data through it, we can use different algorithms to identify which weights and biases are out of whack and adjust them. As we adjust them, we will get closer to finding the optimal set of weights and the optimal network that will provide the best predictive ability on new data. And then finally, as we train this network up, we need to ensure that it doesn't become overfitted to the training data. We need to make sure that it still has the ability to recognize new data and correctly train it, and correctly recognize it. So, how do you actually go about this process? Well, as we've already talked about, it really is an iterative experimental process. So the first thing you need to do is lay out your network. That is, how many layers will it have? How many nodes in each layer? Which functions will you use to optimize on? How will you train it? Which activation function might you use? And each of these typically has its own parameters that you also need to train. So that's step one, building out and laying out the network. The next step is to run your data set through it. And typically what you'll do is take 70% or so of the data that you have available and train it with your new network. You'll then take the remaining 30% of the data and run it through in a prediction mode, and that will help you identify whether your network model is actually any good. It will help you identify the accuracy of the model that you've built. And then you'll repeat those three steps. You'll regenerate a new model based on a different set of parameters or structure. You'll retrain it, you'll retest it, and you'll compare until you identify the best model for your scenario. And then if you think the model is good enough, you can put that into production. You can expose it as a web service and use it to predict customer data. Now, you might be thinking, based on our discussion so far, that there is a no for every single input, that complex classifications like voice or images with millions of pixels will become particularly computationally expensive. Training a network with millions of inputs and hundreds of millions of hidden nodes is going to be very, very difficult. So there are different approaches for these more complex data types. For example, convolutional neural networks are designed for image processing. So rather than doing it pixel by pixel, it can actually extract key aspects of the image and train a model around those. For example, it can detect edges, colors, vertices, and use that information rather than every single pixel. Similarly, for language processing and other data that is time sensitive, that is a time series, we can use recurrent neural networks. And the defining characteristic of this particular network type is that there is a loop. So that means the previous data point can actually influence the classification of the next one. So that's a little bit of an introduction to the basics and the principles of neural networks. Microsoft has a solution to make this process easier called Cognitive Toolkit. It's their open source deep learning toolkit. It has its roots in Microsoft research and specifically in speech research. It's now developed as a product in the open on GitHub, so you can see all of the issues and all of the changes yourself. You can also see that they've started to take external contributions from some of the leading researchers in the field. There are a number of characteristics that make Cognitive Toolkit a really great solution to building neural networks. First, it's relatively easy to use. I use ease in quotes here because neural networks, as we've already seen, can be quite complex and require a good understanding of mathematics and neural network theory. However, it uses a declarative model to build your networks. So you can declare the structure and the parameters, and it takes care of the rest. The next attractive feature is that it's both fast and scalable. It is a highly optimized training network. So that means it will get the most out of hardware that you have. But it will also scale out across multiple nodes to parallelize the training. And then finally, it's a very flexible toolkit. You have a bunch of different options in terms of the languages that you use to interact with it. You can use C#, you can use Python, you can use C++, you can even use Keras. Now, Cognitive Toolkit is not the only deep learning toolkit on the market. There are a number of others: TensorFlow, MXNet, Torch, Caffe, just to name a few. The numbers that you see here on screen are benchmarks conducted by an independent organization. Now, as you can see here, that the Cognitive Toolkit performs particularly well. In this table, it's referred to by its old name, CNTK. My point here is not to convince you that CNTK is better and faster than every other toolkit, because every month these technologies evolve and these numbers will change, and for your use cases they could be very different. However, I think it's clear to say and fair to say that Cognitive Toolkit is a highly performant choice for building your deep learning solutions. So, where is Cognitive Toolkit being used? Well, it has its roots in Microsoft's research team. They used it as part of their ResNet architecture to provide their award-winning solution for image recognition. They also used it when achieving human parity with speech recognition. They have a number of different partners, including Cray supercomputers and NVIDIA, that have worked to ensure that this toolkit works exceptionally well at scale. They've also used it in a number of public-facing scenarios. They've used it in consumer technologies to detect how old people are or to caption photos automatically. They've used it with their partners in smart refrigerators to identify the contents of a refrigerator. They've used it to enable translation scenarios. And they've also used it with partners to identify tumours in medical imaging. So this is a service and now a product that is really proven in production by a number of different groups. In addition to these public offerings, it's also powering a number of Microsoft's biggest services, from Skype and Xbox through to Cortana, HoloLens, and ongoing research efforts. So, how do you get started with the Cognitive Toolkit? Well, the good news is that as long as you have a reasonable understanding of mathematics, then the documentation is really very excellent. They have a number of great tutorials, examples, and more to get you started with various concepts in neural networks and the Cognitive Toolkit. By far, the easiest way to get started is to provision a data science virtual machine in Azure. This is a virtual machine template that Microsoft maintains. It has a whole bunch of different toolkits installed, and it's not just Cognitive Toolkit. A number of the other deep learning frameworks are also available on that machine for you to work with. So you can start working with a range of these tools very easily. The other way to get started really easily is through Azure Notebooks, available at notebooks.azure.com. A number of the Cognitive Toolkit's team's samples and tutorials are actually available there and available for you to interact with without having to provision anything up front. However, if you do want to get started on your local machine, you have a couple of options. The first thing to know is that Cognitive Toolkit considers both Windows and Linux first-class citizens, so they release and support all of their features on both. You can install on either of these platforms in a CPU or a GPU optimized build. And obviously for more serious deep learning tasks, you'll want to find one that supports GPUs. You can also run these as Docker containers. And in fact, on Mac OS, that's the only option that you have. You need to use a Docker container, and unfortunately, GPU acceleration is not available on that platform at the moment. Once you've started and finished your experimentation and want to start productionizing your models, you can look to the Azure platform and services like the Azure Batch AI training service, which helps spin up significant compute resource, either CPU or GPU, to train your models far faster than you could do locally on a single machine. Interacting with this service can be done in a couple of different ways. You can simply write normal code. You can write normal .NET code, you can write normal Python code and simply interact with it directly via the API layer. Or, as we're going to see in just a moment, you can spin up a Jupyter notebook. This provides an interactive experience to build your deep learning models. If you're not familiar with Jupyter, I kind of consider it like Power BI for developers. You can actually write code in an interface, execute it right there, and see the results in that same interface. And those results can be graphs, tables, or raw output. One of the really nice things about the Cognitive Toolkit is that it's focused on a declarative programming model. So translating from the mathematical representation of the model to code is actually relatively straightforward. In this case, we have a mathematical representation of a two-layer hidden network. We see the weights, we see the biases, we see the loss function. Translating this into Cognitive Toolkit is relatively straightforward. We can declare our model in a very similar way to the mathematical representation. Cognitive Toolkit then takes that declarative model and turns it into a graph, which enables it to parallelize and efficiently train it when it's exposed to data. So with that said, let's go and have a look at the Cognitive Toolkit in action. So in this demo, we're going to build a neural network using the Cognitive Toolkit, or CNTK. Before we do that, I'd like to take you through the setup process so you can run something similar on your own machine. Now, as we discussed, the best platforms to run CNTK on are Windows and Linux. There are detailed setup guides for both. If you're on Mac OS, then I'd recommend looking at a Docker container. And again, there's a setup guide for that too. So to set things up on Windows, Python is the easiest way to get started. You'll see on the setup guide here, you just need to select the platform that you want to work with. So the first decision is which version of Python are you running? Are you running the 2.0 or one of the 3 series releases? And then you need to choose your flavor of CNTK. For a VM like I'm running on here, I'm going to use the CPU only flavor because I don't have access to the graphics card. However, if you're running this natively, then I'd recommend picking up one of the GPU distributions, assuming you have a graphics card, because the training process is going to be a lot faster. Now, before you select your GPU option, there are actually 2 options to consider for GPUs. The first one is the plain GPU option.
That's the safe one. And then the other one is the GPU 1-bit stochastic gradient descent option. Now the license across this particular offering is a little bit different, so you might want to review that before you jump into it. The other thing to consider is that you'll really only get benefits out of this option if you're running across multiple GPUs or potentially multiple servers. So it's likely to be a more advanced scenario. So safe options are really either of the first two, CPU only or GPU. So once you've selected the right Python version and the right CNTK flavor, select the URL, and then you can pass that to pip. So pip install, and then the URL, it'll install all of the dependencies that you require to run CNTK on your machine. Then you can quickly test your installation here. They've got a little snippet you can copy and paste into your prompt. And if that returns a version number, then you're correctly set up and start running CNTK. Now, the last thing to do, if you want to actually repeat some of the materials I'm about to show you, if you scroll right down to the bottom of this Getting Started guide, you'll see that there's this instruction here, Python CNTK sample installer. And this is going to install all of the tutorials on your machine. And it's also going to set up Jupyter, which we're going to be using in the next step to actually run some of these demos. So this will set up an entire environment for you to start playing with all of the different capabilities of CNTK. As we mentioned when we introduced the Cognitive Toolkit, there are some really great tutorials available. And you're going to get access to all of those simply by running this command. So with that said, let's go and have a look at the demo or the example that we're going to present today. We're going to be using a very common data set in machine learning, and it's called the Modified National Institute of Standards and Technologies database. And it's a collection of images of handwritten numbers. Thousands of different handwritten numbers that have been packaged up for use and evaluation of different machine learning approaches. So we're going to use CNTK to try and build a model that can classify these numbers. And to do that, we're going to use Python and we're going to use Jupyter. So if I switch over to my console, I'll give you an example of how easy it is actually to start running with Jupyter. You just have to switch directories into the tutorials folder, which will be created as part of that last command that we saw on the Getting Started guide. We type Jupyter Notebook, and it starts a local web server. It'll actually open the browser automatically, and you'll be able to start working with Jupyter. And once you're done, just press Control-C, and it will shut everything down. So let's jump into the Jupyter window. You'll get a directory listing. You'll be able to select from any of the tutorials or examples that are available from the CNTK team. And when you click on one, you'll get an interface like this. And if you're not familiar with Jupyter, the concepts are pretty simple, right? You have a long list of cells in this notebook, and each cell has a different type. So in this example here, the very first cell you see is actually Markdown. The next cell that you see is code, and in this case, it's Python code. Now, these cells can be executed individually, so it's an interactive experience. You can execute them all in sequence, or you can just execute individual cells. So it's a very iterative development process. And each cell can output a variety of different things. So it can output raw text like this one. It can output images. You can call out to charting libraries. It's a very easy way to gradually evolve your model design process. So what is in this notebook? Well, I've tried to keep it super simple so we can build the good stuff together. The first cell here, I've imported all of the necessary libraries. The next cell, I actually download all of the data set, that is all of those individual images of numbers from the public locations, and I cache them locally. And then finally, I define a function that's actually going to allow me to stream those local data sets into CNTK for the purposes of training. And then lastly, and this is not required by any stretch, this is just an example of one of the data points that exists in the training data. So I picked a random number there and I've rendered it there. So that's an example of one of the training data images, which is in this case is a 3. Now, you'll probably notice that this is a particularly low resolution image. It's 28 pixels by 28 pixels. So that actually simplifies things a little bit. We don't need to use some of those more advanced concepts like convolutional neural networks that we talked about in the slides for dealing with high resolution images. So with that said, let's jump into building a neural network. So there are 3 steps I'm going to take you through. The first one, we're going to design the neural network. The next step, we're going to train it. And then finally, we're going to test it. And hopefully most of these steps will actually match pretty closely to the slides that we've just reviewed in terms of the various concepts that are required to build neural networks. I'm going to be using Python here. The code, however, is super simple. It almost fits on one screen. So hopefully if you're not up to speed with Python, the concepts will still shine through. In fact, the next demo, I'm going to use C#. So if this is all completely unfamiliar, then don't worry, we'll be back to .NET in just a moment. So let's have a look at what's required to define a neural network in the Cognitive Toolkit. Well, the first thing we need to do is define the input and the output layers of our neural network. So the first thing here I do is create a layer of input nodes, and I create 784 input nodes. So that's one input node for every pixel in the image. And then I create 10 output nodes. And these 10 output nodes represent the probability for each number classification. So the first output node is the probability that the input image is a 0. The next output node is the probability that that input image is a 1, and so on. So 784 input nodes and 10 output nodes. The next thing that I'm going to do is just set up the training file to be read in by CNTK. So I'm going to invoke that function that we defined earlier. I specify where that file is. I specify there are 784 inputs and 10 potential classifications for this input image. The next thing is I map some of the streams that get returned by that reader function into a format that CNTK is familiar with. So I define where it needs to look for the features, that is the 784 input pixels, and also where it needs to look for the classification, that is what is this particular image a representation of. With that done, I can actually define the structure of the network. I can actually connect those inputs to the output. So the first thing that I'm going to do in my network is reduce the range of that input. So these are color values or grayscale values. So they range between 0 and 255. As we saw in the example, one of the useful things we can do to build neural networks is to actually redefine the range that we have in terms of the input values. So what we're going to do is take those 0 to 255 numbers and we're going to compact that to 0 to 1. So I'm going to divide every single input value by 255 so I get an input range of 0 to 1. So that's the input layer. The next thing I'm going to do is define the first hidden layer. So that's all of those kinds of weights and biases and perceptrons that we talked about just a little bit ago in the slides. So here we have 400 hidden nodes in the first layer. And you'll see that the H value, that is the input divided by 255, is actually passed in. So I'm actually wiring up that first layer of inputs into that 400 hidden nodes, and then redefining H. The next thing I'm going to do is define another hidden layer, which is another 400 nodes. And again, I'm passing the output from the last hidden layer into this new hidden layer. And then finally, I'm going to define the output layer. So I'm going to define 10 output nodes, which is the probabilities for each of the potential classifications. And I'm going to pass the output of that last hidden layer into this layer. So I have 784 inputs. I divide all of them by 255 to get a number between 0 and 1. I then pass those into a hidden layer of 400 nodes. Those outputs then go into another hidden layer. And then finally, those outputs go into the output layer, which is 10 nodes. I also define a couple of defaults that apply to all of these layers. I define an initialization function, which is going to set the default values for weights and biases to something sensible. And I'm also going to define an activation function. You'll remember that's the capability that gives these networks a nonlinear behavior. In this case, I'm using a function called relu. Now, you'll see in both cases, I don't have to define these myself. These are already available for me through CNTK. I can experiment with the ones that work best for my particular problem. In fact, because of some of the advantages GPUs give us, we can actually experiment with some of these pretty quickly. Finally, we define a couple of algorithms that we're going to use to manage the performance of the network. We're going to define the loss function. The loss function allows us to monitor the behavior of the network as we build it, as we train it. And then finally, we define an error function that's going to define the actual effectiveness of our network. So that's the first step done. So we've defined our inputs, our outputs, our hidden layers. We've made a couple of decisions in terms of the functions that we use within the network in terms of activation and loss. And now it's time to train. So how do we train a network? Well, it may not surprise you to learn there are lots of different ways of training a neural network. And when we talk about training a neural network, we're really talking about tweaking all of those weights and biases until we get a network that is effective at predicting new inputs. So the trainer that we're going to use here is one called stochastic gradient descent. So we'll uncomment that there. That's a particular learner algorithm that's going to allow us to train this network. There are a whole bunch of other algorithms that you can experiment with. So I would advise taking a look at those. They're all documented as part of the CNTK toolkit and available if you install CNTK in the way that we've just discussed. Each trainer can have slightly different parameters. So in this case, we have to define a rate at which this particular learner is going to learn. And then once we've defined our learner, in this case, the stochastic gradient descent, we can pass all of the parameters that we've built so far into a trainer. So the trainer takes in the output layer of the network, the loss function, the error function, and also the way at which it actually should train, which is in this case is stochastic gradient descent. Once we've actually built this, it's time to start feeding some data in, finally. And the way that we feed data into this network for the purposes of training is in miniature batches. So we're actually going to send 64 records at a time through the training algorithm. So all this loop does is take 64 records out of the data set that we have on disk, and you can see that we pass in our input map. So CNTK can understand the two streams that are returned. And then we pass that data into the trainer, and we let that run. Now, because I'm running on a CPU-based instance of CNTK, this can take a little bit of time. It'll take several minutes to complete. And once it's complete, we're going to pass this through a test cycle, which is the next code block. Now, if we have a look at this code, it's actually very similar in structure to the training algorithm. So I'm going to read in the test file. So as we discussed in the slides, we don't use the same data to test and train. We have separate data sets. That means we are about to pass through a whole bunch of data that the network has never seen before, so we can evaluate whether it's effective or not. We define a very similar input map to what we defined a little bit earlier for training. And then finally, we start pushing through those miniature batches like we did for training. So in this case, we're going to push through batches of 512. So that's 512 images we're going to present to the network. We're going to get a result for each of them. We're going to measure the error, that is whether it got it right or wrong. And then we're going to add that to a running counter, which is our result. And then finally, we're going to take that total error, we're going to divide it by the number of records processed, and then we're going to get an average test error for this particular model. And that's going to allow us to understand whether all of the decisions we've made so far have been effective. And if we make a few changes, we can then compare the performance of the network over time. So I'm going to run this now. We're going to pause this screen cap because this will take several minutes, and then we'll return and evaluate the result. And we're back. The notebook has finished executing. It's gone through all of the cells. It's downloaded the necessary sample data sets. It's written them to disk. It's built our network. It's trained our network. And finally, it's tested the network. And the output here is an average test error of 1.84%. So that means roughly out of the test data set, we were able to correctly recognize the number in 98% of cases, which is pretty great for such a short time investment to set this thing up. Now, typically when building machine learning models, we don't just stop at one. We like to experiment a little bit to understand the limits of this particular technique. So we might adjust the learner, we might adjust the parameters to the learner, we might choose a different activation function or change the design of our network, the number of nodes, the number of layers. When dealing with images, however, one of the most effective techniques is convolutional neural networks. And we saw that in action in the slides just a moment ago. So the next step I'm going to take here is actually employ that particular technique and see how it works on this particular data set. Because this is actually built in, it's natively supported by the CNTK framework, it's actually a very simple change that I have to make. So rather than having these two hidden layers of 400 nodes each, I'm going to add in two convolutional layers instead. The rest of the network design doesn't have to change. The last thing I need to do is, because convolutional layers actually understand the concept of image, I have to adjust my input variables. So rather than having an input variable that is one node for every pixel, I can actually represent this in a slightly more natural way to reflect the image. So I'm going to have one channel that is, it's a grayscale image. I don't have multiple color channels, one channel, and then I'm going to have an image that is 28 by 28. And that's it. That's the only change I need to make to actually take advantage of this particular style of neural networks. Everything else can remain the same. My initialization function, my activation function, how I measure loss and error, the trainer, everything else stays the same. So it's very easy to start experimenting with CNTK because all of these different components are largely compatible and will interact very nicely. So we're going to do exactly the same thing. I'm going to stop the screen cap here. I'm going to let this system run. And we're going to return and understand how much better or worse this particular technique might be. And we're back. So our updated network design has been trained. We've tested it, and we now have an average test error of 1.36%. So this is actually considerably better. So just by changing a few lines, we're able to improve the effectiveness of our model. Now at this point, we would continue. We would change additional parameters. We would extend and adapt the design of our network to improve the effectiveness. But in this case, it's time to move on. And the next thing that we're going to have a look at is, how do we operationalize this model? We're really happy with it. How do we actually use it in a production scenario? Well, the first thing that we're likely to do is output that model to a serialized persisted format. And the easiest way to do that is to run a little bit of code. So we can actually very easily, from CNTK, take the model and put it on disk. So we can just go Z, which is our output layer, save, and we give it a name. Just name it the same name as the data set, and we're going to run this particular cell. And that's all there is to it. We now have a copy of that network on disk that we can use in an operational environment. And in the next demo, we're going to have a look at how we can use Visual Studio and .NET to host this model and use it in a production scenario. So we're back in Visual Studio, and now we're going to see how we can operationalize this model on .NET. So on the right should be a very familiar site, and that is the default ASP.NET 5.2 web project. So I have just created it using the file new wizard. It's running on .NET 4.5. It's a very common solution template. The one thing that I do need to do, though, is install the CNTK NuGet package. You can see on the left there that the CNTK CPU only package has been installed to this solution. There's also a package for GPU version of CNTK if you are running on hardware that supports GPUs. Once you've got the NuGet package installed, make sure that you update your build configuration to target 64-bit. You need to make sure that the .NET project compiles to a 64-bit binary, and you also need to make sure that IIS Express is configured to run the 64-bit instance of itself. 32-bit runtimes are not supported by CNTK. This is also something to keep in mind when you go to production. So you'll need to configure IIS or potentially Azure Web Apps to run in 64-bit mode if you want this to work properly. So once you've actually got all of this in place, how do you build a controller that can work with CNTK models? Well, it's pretty straightforward, really. What we're going to build here is a controller that can classify an image, just like we saw in the Jupyter notebooks. It allows our customers to provide us an image, and we will tell them what we believe is the number in that image. Now, for simplicity's sake, I have actually included the image as a variable here. You can see it. We can see all of the different pixel values. It's a grayscale image, 784 inputs, just like we had in the Jupyter notebook. Each value, each pixel ranges between 0 and 255, again, just like we saw before. Now, obviously in a production environment, we would expect our customers to submit these values as part of the HTTP post. We wouldn't hard code them, but for clarity, we can see it just here. So how do we work with the CNTK SDK? Well, I've got my operation here. It's a get method. First thing that we do, as you might expect, is to pull in that model that we serialized at the very end of the last demo. So we find its location, and then we load it using function.load, and that's part of the CNTK toolkit. We also specify that we are wanting to use the CPU to run this model. We don't have, unfortunately, the capability to use GPUs just here. The next thing that we need to do is build some data maps. And these map the input to the image that we see in the variable above. And the key line here is on line 89. What we're going to do is actually map the input to that image. We then build in map, and this is just a completely stock standard .NET dictionary, and it maps the input to that actual value that we've just created. We then do something very similar for the output. We create a standard .NET dictionary which maps the output variable to the value. But of course, we don't know what the output variable is. We pass null instead. That's the whole point of having this model here, is to actually classify this image. So we've got our input, we've got our output all ready to be populated, and we pass it to model.evaluate. So we have our input and our output data maps. And we specify that this is a CPU operation in this particular environment. Now you'll notice that this isn't an async operation. There's less value of async in this particular scenario because this is an entirely CPU bound operation. There's no kind of network waiting. There's no blocking of the thread. This will actively consume all of the resources that it possibly can. So once this completes, it returns, and we'll find in our output data map, instead of having null for the output variable, we actually get the values that the network creates. Now, if you remember back to the design of our network, we have 10 output values. So each node represents one of the numbers between 0 and 9. And the node that produces the highest number is the network's best guess for the number that's contained in the image. So what we have down here is that we find the highest number that any of the nodes produces, and then we figure out which node that was. And this particular code snippet is simple, but not terribly efficient. And that node index is the number that the network is predicting is contained within the image. So we can run this up and have a look. As a little bit of an advanced preview, this particular image that I have encoded up the top here is actually the number 3. So let's see this in action. So I'm going to start debugging. I've got everything set up for 64-bit mode. And then I'm just going to invoke this from PowerShell. We're just going to invoke that get operation. It's going to do the mappings. It's going to invoke the model. And then we're going to break on the breakpoint to see the result. So again, in a production environment, we would expect to actually pass the body as well here. We would, in that body, encode the image. But we have that hard-coded for the purposes of this demo. And if we inspect the result, we'll see that the result is actually the number 3, which is exactly what we were expecting. So in this case, the model was able to correctly identify the number that was contained in that image. We can see that here if we look closely, that the response from that network endpoint is the number 3 and the correct classification of that image. At this point, we're going to go back to the slides. We've seen how we can use Jupyter and that interactive notebook style experience to build and experiment with different model types and iterate quickly to identify better patterns and better approaches for solving problems. And then we've seen how easily we can use .NET to pull that model in, load it up, map it to a new set of data, and expose it as a web API endpoint. Let's get back to the slides.
So in that demo, we just saw how easy it is to get started with the Cognitive Toolkit using a Jupyter notebook, and how we could build a simple number classifier. We also saw how we can host our model in a standard .NET Web API thanks to the NuGet package that's available for the Cognitive Toolkit. So this has been a very high-level introduction to the principles of neural networks and to the Cognitive Toolkit. If you want to learn more about this platform, Microsoft have some really great resources that I'd highly recommend. First is a Deep Learning Explained course on edX. This is actually hosted by a number of the researchers that are responsible for the Cognitive Toolkit and go into some detail about the mathematical underpinnings. There are also a number of excellent videos on Channel 9, and of course this is developed in the open. So all of the source code for the samples and for the application itself is available on GitHub for you to pull and examine. That brings us to the end of our session on deep learning and the Microsoft Cognitive Toolkit. In this session, we've shown you how to use a deep learning framework to build your own neural network models. This will unlock any potential bespoke AI components that you might want to build for your application or in your organization. Now, I say maybe in the slide here because, as hopefully you've identified, this is not an undertaking for the faint of heart and requires a significant investment in time and effort. I hope you've enjoyed this series on the Microsoft AI platform and now have a good understanding of the capabilities that the cognitive services and the Cognitive Toolkit can bring to your applications. Make sure you stay tuned to Channel 9 for more great AI content, and thank you for watching.